This is AP Calculus AB, and in this video, I'm going to go through section 5.3, which your book title is Connecting F prime and F double prime with the graph of F. So I usually just refer to this as F, F prime, F double prime. We're just talking about the relationships between those three functions. So the first part of this, we actually talked about this in section 5.1. I went a little bit out of order with this and talked to you about the first derivative test back in section 5.1. So your book covers the first derivative test in this section. And just as a reminder, when we are looking for maximum and minimum values, and particularly local max and local min values, we can use the first derivative test. And the first derivative test is based on the idea of identifying critical points, which are points within our interval where our derivative is either zero or undefined. And then we test around those critical points to see if our function goes from increasing to decreasing or decreasing to increasing. And that allows us to identify if there's a maximum or a minimum in that interval. So this is just sort of a rehash of the stuff from that I covered in the video for section 5.1. So just as a quick review, it says use the first derivative test to find the relative extrema, and we've got this function x cubed minus 6x squared plus 15. So remember, when we're going to do this, the first thing we need to do is we need to take the derivative. So f prime of x here would be equal to 3x squared minus 12x. And then I'm going to set that equal to 0 to figure out where my critical points are. You can see you could factor a 3x out of this. We'd have 3x times x minus 4 is equal to 0. So we get critical points at 0 and 4. And then I'm just going to use a sign chart to identify whether I have maximum or minimum values at these points. Okay, so I've got the values of 0 and 4 on a number line here. This is my sign chart for f prime. So remember, we can just test within one of these intervals and then use the multiplicity of our critical points to figure out if we have sign changes. So the interval from 0 to 4, I'm just going to use 1 because that's an easy number to test. And I would plug 1 into that first derivative. Obviously, I'm going to get a negative value. So that means in this middle interval here, I'm going to have a negative, which means the function's decreasing. And I had a multiplicity of 1 for each one of these critical points, so I know there's going to be a sign change there. And now from that, I can tell that there is a local maximum at x is equal to 0. And I'm going to give the actual function value as well. So it'd be f of 0 is equal to 15. And there's a local minimum at x is equal to 4. And that would be the function value f of 4 is equal to negative 17. Okay, so I'm going to mention this later on in the notes. I've got it written out later on, but I want to just go through this now. If you have a problem like this and you are asked to justify your answer, keep in mind that the sign chart does not serve as your justification. What you need to do in order to justify your answer here is, I would say there is a local maximum at f of 0 equals 15 because the function goes from increasing to decreasing at that point, or I could say because the derivative went from positive to negative at that point. And then we could do the same thing for the minimum. So keep that in mind. If you're asked to justify, you actually have to write out a sentence that justifies why you know from the first derivative test that there's a maximum or a minimum. All right, so let's move on here and talk about something called the second derivative test. So the second derivative test is another way that we can find maximum and minimum values. It's actually based on the idea of concavity, which we haven't really talked about yet, but I'm going to go through a little bit with you here. So you may have seen concavity a little bit back when you were in pre-calculus. Concavity is just a way of indicating what's happening with our function in terms of the derivative value. Is the derivative value increasing or is the derivative value decreasing? And if you look at these two graphs that I have here, when a graph is concave up, you can sort of think of it as having like a parabolic shape opening up, or concave down, think of a parabola that opens down. And from the standpoint of the second derivative, if I have a second derivative that is positive, that makes my graph concave up. When the second derivative is positive, that means my derivative is increasing in value. So that makes my graph concave up. And then when I have a second derivative that is negative, that's going to tell me that my first derivative is decreasing in value, and that's what makes it concave down. Now, for the second derivative test, what we're really looking for is how do we identify if there's a maximum or a minimum? So this test only works when I have points where the derivative is equal to 0. So this doesn't work for the critical points where we have those undefined slopes. It only works for the critical points when we have a slope of 0. Sometimes those are referred to as stationary points. I don't really use that terminology, but you will see stationary points sometimes used to indicate derivatives that are equal to 0. So that's what we're going to do, is we're going to identify where's our derivative 0, and then we're going to figure out what the concavity is at that point. If my second derivative is positive, that means we're concave up. So this would be an example where I have the derivative 0, second derivative is positive, and you can see then that is where I'm going to have a minimum value. If the second derivative at one of those 0 derivative value points, if the second derivative is negative, you can see that's going to create a maximum. So you're just thinking about, is the graph opening up or is the graph opening down based on that second derivative? Now, if we get a point where the second derivative is 0, then that means this test isn't going to give us any information, and we would have to use a different test, like, for example, the first derivative test. All right, so let's go through an example here, and then I'll have you try one of these. So this says use the second derivative test to find the relative extrema. So when you use the second derivative test, it starts out in a similar way to the first derivative test. I'm going to take my derivative. I'd get 3x squared minus 12. I'm going to set that equal to 0, and I'm going to solve for x here. And what I would find is x is equal to plus or minus 2 in this case. Now, where this starts to deviate away, if this were a first derivative test, we would just do a sign chart. Well, I'm not going to do a sign chart here. I'm going to look at my second derivative. So my second derivative would be 6x. And what I'm going to do is just figure out, based on my second derivative, is my graph concave up or concave down? So for example here, my second derivative at negative 2 would be negative 12. And that's less than 0, which indicates that my graph is concave down. And if I take the second derivative at 2, I get a value of 12, which is greater than 0, which indicates that my graph is concave up. So based on the information that I'm seeing here, my critical points, those were the points where the derivative was 0, and the information that I have here, I can use that second derivative test to say, okay, well, I know that since my graph is concave down at negative 2 and it has a 0 slope, there's going to be a local maximum at x is negative 2, and that would be the function value f of negative 2 is equal to 11. And then in a similar way, I can say there's a local minimum when x is 2, and that would be the point f of 2 is equal to negative 21. So it's not that difficult to do, but the main thing is we have to show that we have points where the derivative is 0. We have to show whether our graph is concave up or concave down at those points based on the second derivative, and then from there we can conclude whether we have a maximum or a minimum. So I showed you a pretty simple example. What I want you to do is try this next one. You can use that first one as a model, but try this next one where we have g of x equals x squared minus 3 times e to the x, and use that second derivative test to determine whether you have a maximum or a minimum at those points where the derivative is equal to 0. So you can pause the video, work through that problem. When you come back, I'll show you the solution. Okay, so here's what you should have come up with on that one. So you can see that the first thing I did was I took my derivative, I factored e to the x out, and I got to this point where I've got e to the x times x squared plus 2x minus 3 is equal to 0, and then I factored that quadratic expression into this. Now e to the x is never going to be 0, so I only get 2 critical points at negative 3 and 1. And then the next thing I'm going to do is I'm going to take my second derivative. So it works out in sort of a similar way. I ended up getting my second derivative in this form, e to the x times x squared plus 4x minus 1. Now I've got to figure out, is my second derivative positive or negative at each one of these 0 derivative points? So I found the second derivative at 1, and I found that it was greater than 0. Notice here I never actually found the value. I just substituted in and realized, okay, this is going to be greater than 0. Because I don't need the number, I just need to know if it's positive or negative. Same thing with the value at -3. I found that it was less than 0. And based on that, you can see there's a local minimum at the point where x is equal to 1, and the y value there would be -2e. And then there's a local maximum at the point where x is equal to -3, and I have a y value of 6e to the -3 power. Okay, so second derivative test we don't usually use so much in this manner. Where we usually use it is just when we're given limited pieces of information about what's happening with our function. So if all you knew about your function was that it had a derivative of 0 at a point and it had a second derivative of 5 at a point, you can conclude based on just that information that there's going to be a minimum at that point without even knowing what the function is. All right, so let's move on here and talk about finding extreme values on closed intervals. Now, when we talk about extreme values on closed intervals, it's a little bit different than when we do the local max, local min, first derivative, second derivative test type of stuff. When we're looking for extreme values on closed intervals, we're going to use what's called the extreme value theorem. And the extreme value theorem is what tells me that if I have an extreme value, meaning like a maximum or a minimum point on some interval, I know that that's going to occur at a critical point. And the other part of it is if it's a closed interval, I know that an absolute max or an absolute min has to occur at a critical point or an endpoint. So those are the things that I need to check when I'm looking for extreme values on closed intervals. So let's go through a couple of examples here. This is something that's pretty simple, but it's also very, very important from the standpoint of how do you write your solution out and how do you justify your answer in these cases. So it says find the absolute maximum and minimum values of the function on the given interval. And we have this function x cubed minus 3x plus 1. We're looking at the interval 0 to 3. Okay, so what I'm going to do here, remember, we need to look at critical points and endpoints. So I'm going to take my derivative, and I'll get 3x squared minus 3. I'm going to set that equal to 0, and I would get points of 1 and -1 that are my critical points. Now, I need to account for all the critical points and all of the endpoints. So I'm going to use what's called the candidates test. The candidates test is just basically a table that is going to allow me to test out all of my points and make sure that I've identified these are all the possible points where the absolute maximum or the absolute minimum could occur. And then in addition to that, I'm just going to find the values and then I'm just going to compare them. Now notice in this case our interval is 0 to 3. So this critical point I have at -1, I don't really need to be worried about that point because it's not going to be accounted for on that interval 0 to 3. So what I'm going to do is list out my endpoint of 0. I had a critical point of 1 and I have another endpoint of 3. And then just use the original function. So at 0 I have a function value of 1. At 1 I have a function value of -1. And at 3 I have a function value of 19. So just based on that table, I can say the absolute maximum is going to occur at f of 3 is equal to 19. And I can also say the absolute minimum is going to occur at f of 1 equals -1. And I know that because the only points where the absolute max or the absolute minimum could occur are the critical points and the endpoints. And I've accounted for all of them. Okay, so in terms of justifying your answer, I told you with the first derivative test, you actually have to write out a statement. When it comes to finding extreme values on closed intervals, that table that I did there, this table, my candidates test, is my justification because I am showing to the person that's looking at my work, I have accounted for all the possible places where the absolute max or the absolute min could occur. So I don't have to do any writing. I don't have to write out any sentences. I don't have a long justification. This is my justification. So keep that in mind because you're definitely going to see that down the road. Use that candidates test when you're finding max or min values on a closed interval. Okay, so I have another one here for you to try. And it's this one right here. We have f of x is x to the fourth minus 2x squared plus 3. We're looking at the interval -2 to 3. So same thing, I want you to pause the video, work through this, use your candidates test, and from that, figure out where the absolute maximum and absolute minimum points are. Okay, and here's what you should have come up with on that one. I took my derivative, I set it equal to 0, I got it into a factored form, and there were actually 3 critical points, and they're all within my interval -2 to 3. So I set up my table this time, and in my table, you can see that I've got -2, 11, -1, 2, 0, 3, 1, 2, and 3, 66. And all I'm going to do is identify, okay, which one's the highest point? That's the absolute maximum. Which one's the lowest point? That one's the absolute minimum. And I'm just comparing the function values there. Notice there's 2 points where there's an absolute minimum. There's 1 point where there's an absolute maximum. And again, that table that I put in there, that's my candidates test. That serves as my justification. Okay, so when it's a closed interval, that's all we have to do. Just a reminder, when it's an open interval or we're looking for local max or local min, we have to write out a statement that justifies what we're seeing in our sign charts. So closed interval, just use the candidates test. When we're looking for local max and local min, then we're going to have to go through and we're going to have to use an actual statement justifying our use of the first derivative test, or even if we did the second derivative test. All right, let's move on here to the idea of testing for concavity. So we talked about the second derivative and how it represents the concavity of the graph. This is just reinforcing that idea. You can see on these graphs over to the right, I told you when the graph is concave up, the derivative is increasing in value. Look at these tangent slopes here, and you can see how they're increasing in value. So clearly, I've got a graph that's concave up because the second derivative is increasing in value. The rate of change of the first derivative is positive. Okay, same thing when I'm concave down. You can see I started with a positive slope, and then it's becoming negative, and then steeper in the negative direction. So my derivative is decreasing in value. That's what creates that concave down shape. So that's all we're really looking at here is how do we identify where the graph is concave up or concave down. And then we have one other thing here called a point of inflection. Those are points where the concavity of the graph switches from concave up to concave down or concave down to concave up. So when we look at points of inflection, we'll look at where's the second derivative 0 or potentially undefined, but typically 0. And then we just test around those points. And we look for sign changes indicating that the derivative's going, or the graph is going from concave down to concave up or vice versa. Okay, so let's take a look at an example, and then I'll have you try one of these. It says, use the test for concavity to find the points of inflection. And we have this function again, x cubed minus 12x minus 5. So I'm going to take my derivative, and that would be 3x squared minus 12. I'm only interested in concavity, so I don't really need any other information from the first derivative. I just need to use it to get to the second derivative, and the second derivative here would be 6x. Now I'm going to take my second derivative and set it equal to 0. It's sort of like critical points when I'm dealing with the second derivative, but I'm looking for possible points of inflection. So I got x is equal to 0. And I need to find out, is this actually a point of inflection? Well, if necessary, I can do a sign chart. In this case, I'll explain here in a second. I don't really need the sign chart, but I'll show you how I can use it. So just like we did the sign chart with the first derivative, I can do the same thing with the second derivative. So to the left of 0, I can see that I would get a negative value. I'm looking at this second derivative. I can say that there's a negative value here. And then to the right of 0, there'd be a positive value. So what that graph tells me is that to the left of 0, my graph would be concave down. To the right of 0, my graph would be concave up. All they asked us for here were the points of inflection. So usually I use the acronym PI for points of inflection. I have a point of inflection at x is equal to 0. They didn't really make it clear if they just want the x value, so I'm going to go ahead and find the point. That would be when x is 0, the function value is negative 5. So that's my point of inflection. Had this question said, list the intervals where the graph's concave up or concave down, you could see here that it's concave down from negative infinity to 0, and it's concave up from 0 to infinity. Okay, so that's really all there is to it. It's not that difficult. Obviously, the derivatives could be messier. The algebra to solve for those possible points of inflection could be messier, but it's pretty easy to do. And just like we did with the first derivative test, I can use the multiplicity of those points where the second derivative is 0 to know if there's going to be a sign change. Here, there was only one point of inflection, and it had, or one possible point of inflection. It had a multiplicity of 1. So I already knew that it was a point of inflection based on its multiplicity. So really, if you know the multiplicity, you can tell right away if you have points of inflection or not without even using that sign chart. Okay, so here's another one I want you to try. We have y is equal to e to the negative x squared. And again, this is a little harder, but it's the same general idea. I want you to find those possible points of inflection and go ahead and do the sign chart just so you can look at the concavity of the graph. But really what the question is asking you to do here is find the points of inflection. So pause the video, and when you unpause it, I'll show you the solution. Okay, so here's what you should have ended up with on that one. I took my derivative, and then I got my second derivative, and my second derivative factored into this e to the negative x times 4x squared minus 2. E to the negative x is never going to be 0. So I just solved that 4x squared minus 2. I set that equal to 0, and I got x is equal to plus or minus the square root of 1/2. Okay, so then from there, I went ahead and did my sign chart. And in my sign chart here, you can see that I had values at negative square root of 1/2 and positive square root of 1/2. So what I did to test this was I just tested 0, because that's in that middle interval. Now, it's easiest if you use these factored forms of your derivatives when you're trying to figure out if your derivative is positive or negative. In this case, is the second derivative positive or negative? I know e to any power is positive. So really, I just need to look at this part of it. If I plug 0 into that, do I get a positive or a negative? I get a negative. So I know the end result here is going to be negative on that middle interval. And then since they each have a multiplicity of 1, I know there's a sign change. So my graph is concave up from negative infinity to negative square root of 1/2, concave down from negative square root of 1/2 to square root of 1/2, and concave up from square root of 1/2 to infinity. All right, so we were looking for points of inflection. So you can see I just listed out, I knew that there were points of inflection where x is plus or minus the square root of 1/2, and we get the same y value here because it's got an x squared in our expression for the function. So I got the same y value for those points of inflection. Okay, so one thing I want to point out here really quickly when we're looking at points of inflection, this is a problem that I put in here because I want to make sure that people are really clear that you have to either take multiplicity into account or you have to do a sign chart. So I've got y is equal to x to the 4th, and I'm trying to find points of inflection. So I'm going to start by taking the derivative here, and I would get y prime is equal to 4x cubed. Remember, we need to be looking at our second derivative, so that would give me 12x squared. When I set that equal to 0, I get x is equal to 0. But the thing to remember about this is that that would actually be a double root. So the fact that that's a double root automatically tells me there's not going to be a sign change here. But if you want to verify that, you could always go through and do a sign chart and check the second derivative. If I plug a negative number into 12x squared, I'm still going to get a positive. If I plug a positive number into 12x squared, I'm going to get a positive. So this is telling me that this graph is always concave up. And if you look at the graph to the right here of f of x is equal to x to the 4th, you can see that the graph is always concave up. So be careful about that. Don't just set the second derivative equal to 0 and assume that all those points that you find are going to be points of inflection. You have to either take multiplicity into account or you have to do a sign chart. All right, so we're going to spend a lot more time on this section next time. So we still have to talk about how do we put all this information together to interpret what the graph of a function would look like. But what I want to do here is at this sort of midpoint of this section that we're in, I want to go through a couple of AP examples and show you how these would work. So this is an actual old AP test question. and this was on the non-calculator section. It says the maximum value of the function y is equal to -4 square root of 2 minus x would be what? So what I want you to do is pause the video and try to solve this out, and when you come back, I'll show you the solution. Okay, and here's what you should have ended up with here. So they asked for the maximum value of the function. So there's a couple of things about this. What I started with was I went through and I said, okay, let me take my derivative here, and I ended up, when I simplified it down, into this form. I got it into this form right here. 2 over the square root of 2 minus x. Now, think about that value. No matter what I plug into that, I can't plug x is bigger than 2 or even equal to 2 in there. But no matter what I plug into that, I'm going to get a value that is positive. So that's telling me that my function is always increasing. Well, my function is always increasing. I went back and I thought about this function, and I said, okay, looking at that function on that original -4 times square root of 2 minus x, what would the domain of that function be? Well, the domain of that function is -infinity to 2. And I'm not really that concerned with exactly what this function looks like, but I know this graph is always increasing until I get to the right endpoint. And then that's going to have to be my maximum value because the function is always increasing. So I know the maximum value is going to occur when x is equal to 2. Okay, so that's the first thing. I know where the maximum value occurs. Now, the next thing is, notice the question doesn't say find the x value where the absolute maximum occurs. It just says find the maximum value. And when they say that, they're referring to the function value. So notice 2 is here, but that's not what I want. I don't want the x value. I want the function value. So I plug 2 back into this original function, -4 times square root of 2 minus x, and I get a function value of 0. Okay, so that's really the type of question that you might see on the AP exam. And you can see how it's still using the same ideas that we talked about, but sometimes you've got to think through exactly what's happening with your function. So that means that we have to have a good conceptual understanding of what all these things are meaning. What does the first derivative actually mean? Why is the interval important? Looking at the interval notation, how do I know that there's an absolute maximum at the right endpoint? So all of those things are important, and we have to be able to reason through those things. It's not that the math here is that difficult to do. It's actually fairly simple. It's the actual conceptual understanding where you might get tripped up a little bit. Okay, so there's one more of these that I want to show you, and we're going to spend some time working with the calculator next time. But I just wanted to show you this to give you an example of how you really have to understand how these relationships are working. So this question says the derivative of the function f is given by f prime equals x squared cosine x squared. How many points of inflection does the graph of the function have on the open interval -2 to 2? Now, we haven't used calculators a whole lot in here yet. But what I want to warn you about is we're going to start using them more. And when you have these types of questions and they're intended to be calculator questions, typically there's little to no work that you're actually going to do. These are typically going to be purely conceptual questions. So what they're wanting us to do here is look at the graph of the derivative and use that to figure out how many points of inflection I have. And I will show you what my graph looks like here. Okay, so here's my function. And I've plotted it just for now on the open interval -10 to 10, but they asked us to use the interval -2 to 2. So I'm going to adjust my window here and go -2 to 2. Okay, so this is what my graph looks like. Now, when I'm looking at the graph of the derivative, I have to be thinking about how to identify concavity from the graph of the derivative. So remember, the derivative is the second derivative is the slope of the first derivative. So when I'm thinking about concavity, I'm thinking about the slope of this graph. See how it's decreasing here? That means my graph is concave down. Then it's increasing, it's concave up, and then concave down, concave up, and then concave down. So what I'm really looking for are changes in direction for my derivative graph. So here I would have 1, 2, 3, 4, 5 points where my graph changes direction, the graph of the derivative. that means there would be 5 points of inflection. So that would be one way to do the problem. Now, another way I could do this, let's say you weren't really sure about that whole idea. Now, we're going to practice with this idea of investigating these graphs a lot more next class. But another way you could do this is we could graph the derivative of this function. So I'm going to do the derivative of the y1 function, and I'm going to evaluate that for all values of x. Okay, now the graph that I really want to be looking at here is just the second derivative. The problem with doing it this way is my calculator has to approximate the second derivative graph. And you can see that it did it here fairly quickly because we had a nice, fairly nice simple function to work with. But from the standpoint of what am I looking for on this? Well, now I'm looking at the second derivative. So think about your sign chart. For the second derivative, when I'm looking for points of inflection, I'm looking where the second derivative is changing from positive to negative or negative to positive. So all I have to do is count how many times I cross the x-axis here. 1, 2, 3, 4, 5. Okay, so also that gave me 5 points of inflection. So let me turn this other graph on, and you can see how these two graphs are related to each other. So this point where I had a minimum on the f prime graph, notice that that's a point where it crossed. This point where I had a maximum, it crossed, and so on. So you can look at the first derivative graph or the second derivative graph to come up with your solution there. But the main idea is when you're solving these things out, we're really not doing a bunch of work and doing all of these tests by hand. We're just interpreting from the graph the same information. So this one would have had an answer of 5. Okay, so as far as the homework goes, you might find some of this to be a little bit challenging at first, but the big thing is really get the ideas of the first derivative test and the second derivative test and the test for concavity down. And that way, when we start converting that over to looking at these from a graphical perspective, it'll make a little bit more sense to you.